Hey class, this is screencast for notes 15.6 and 15.7. So this will take just a little bit of time to talk about Le Chatelier's principle and the reaction quotient. So the first one is Q, the reaction quotient. So I'm going to have to repeat myself several times. I apologize for that in advance because students tend to really overthink the reaction quotient. You guys know already what K is. K is these values. You remember we talked about the A, that would be C and D, sorry, concentration of C and D, just like this, and that would be A and B there. Okay, you've seen this before. This is what K equals. As it turns out, Q is exactly the same thing, just not at equilibrium. So I have the same thing here. I have C to the exponent of C, where C is the small c is the coefficient. Exactly the same thing as D. Exactly the same thing as our equation for K. I'm going to write the same thing down here. This. The only difference is that Q may not be at equilibrium. Okay? So that's our 1L. There we go. There we go. Okay. So Q may not be at equilibrium. So K and Q are the same equation, except K is at equilibrium. That's the only difference, at equilibrium, and Q may not be at equilibrium. We're not sure if it is or not. So what we can do then is we can compare K to Q and see if we get equilibrium or we get something different. So take a look. How a system is at equilibrium. So if I have, here we have equilibrium. Notice that K and Q are the same number, right? The same constant. So what happens if I have Q is less than K, as in this side here? That means our reactants form more products. Okay. If Q is greater than K, as we have over here on this side, then the reaction forms more reactants. So it's just a balance as to like what is Q. Q would be given to us, or we would have to figure out what Q is, and then we would compare it to K, and that would tell us like which way the reaction is going to go. Okay, so here's another screen that explains exactly what I just said. If Q is larger than K, then equilibrium will shift to the left, which means reactants. Okay, that's what that means. It shifts to the left to form more reactants. If Q is smaller than K, then it shifts to the right to form more products. Okay, that's all that means. So Q is actually a pretty easy thing. Once we know what K, the formula for K is, that expression, we know what Q is automatically because it's the same expression. We're just not sure if the concentrations are at equilibrium or not. And that's why we do like the same calculation to figure out if it's equilibrium. Now that was 15.6. Now let's talk about Le Chatelier's principle. So Le Chatelier's principle basically says is that a system at equilibrium is disturbed by a change, temperature, pressure, or concentration of the components. The system will shift its equilibrium position as to counteract the effect of the disturbance. Almost like it's very similar to when you have somebody balancing something. You have two things here, one thing on either side, and then if you increase by putting another thing here, then that means that this will shift just a little bit this way to get them still to be equal on both sides. That's what Le Chatelier's principle basically says, is that the system will readjust so it will stay balanced, which is what we're talking about. So here's the transformation of nitrogen and hydrogen into ammonia. This is called, I forget what it's called. Oh, it's right at the top. Hot air process. The hot air process happens at like 5 atmospheres because you need an extremely high pressure scenario to get nitrogen, hydrogen together to form ammonia to use it for fertilizer. So the hot air process looks like this. You can see nitrogen, you can see hydrogen, and then you can see what happens when we move something or we increase or decrease. In this case here, we decrease the amount of hydrogen as it says H2 added at this time. And then the equilibrium will adjust. You see where the equilibrium is for hydrogen, for nitrogen, and for ammonia before, and now see where it is now for hydrogen, for nitrogen, and for hydrogen and nitrogen down here, and then ammonia in the middle. You can see that both the ammonia, if I increase this, this decreases and this increases. Okay, and that's what we're seeing here. So that means that if I increase hydrogen, that means the reaction must balance by moving towards more products, which is why this increases over here. This one gets used up more, which is why that decreases. So, and this one also, the hydrogen also decreases after the initial addition. So the initial addition right here, let me get rid of some of this stuff so you can see it. The initial addition of concentration goes up to here and then balances back down again. Notice that the initial condition for nitrogen decreases as it produces more products. Okay. So let's keep going here. That's just one case where we add something to one side and then figure out which way it's going to go. Okay, that's just a detailed diagram of the Haber process. Lots of fun. This one doesn't really matter to us either, the effect of changes on temperature. So when we increase a temperature for a reaction, it matters whether that reaction is exothermic or endothermic, all right? So what we can do is we can actually, I'm going to keep going here. What we can do is we can actually use, this doesn't talk, okay, so I'm going to back up. Sorry guys, I should have used a different set of screens. So what we can do in this situation here where it says the effect of changes is if we have an exothermic reaction. Exothermic means giving off heat. Then we can add heat to this side over here. If we increase the temperature, that's going to increase the heat and it's going to force the reaction back in this direction. In other words, if we have an exothermic reaction, but we increase the temperature at which that reaction is happening, it actually produces more reactants or shifts the balance towards reactants than it does towards products. If we have an endothermic reaction, endothermic means the reaction absorbs heat, then heat actually acts more like a reactant here because you need the heat and then the other two reactants to get the reaction to go. And then if we increase the temperature, that means we're increasing the temperature over on this side, and that uses more of this and uses more of this and forces our equilibrium to the right. This increases and this increases. So temperature increase for an endothermic reaction where the heat ends up as a reactant forces more products. Exothermic, when you increase the temperature, the heat then is over on the right-hand side and it produces more reactants or shifts the equilibrium to the left. Okay? These are all kinds of things that we're going to talk about. A catalyst. What does a catalyst do? Excuse me. A catalyst increases the rate of both forward and reverse reactions. So a lot of times what it does is decreases the energy it takes to go forward. Because you go up like this, but the forward reaction and the reverse reaction coming back this way is also affected. So equilibrium is achieved faster, but the equilibrium composition remains unaltered. So in other words, the catalyst doesn't actually change where the equilibrium is, it just gets there a lot faster. And that's it. Pretty simple stuff. We'll go over many more problems for Le Chatelier's principle because that's where you're going to see a lot of extra questions on the AP Chem exam. So I want to make sure you're ready for that.